Okay. So, today we will start with the section of a rational number or cut. Section of rational numbers, or we also call it cut of rational numbers. Now, we have already seen that if a rational number is given p by q, where p and q are integer, q is positive and there is no common factor in it, then between any two rational number one can introduce another rational number. In fact, infinite number of a rational number can be introduced in between that, and with the help of the sequence of the rational number one can generate the irrational number, and entire class of the rational number can be divided into two parts, rational roll class and the upper class. Is it not? Just like we have seen the set of all rational number which are less than equal to 1 and the set of rational numbers which are greater than 1. So, one divides the whole set of rational number into two parts, those which are less than or equal to 1 and those which are greater than 1. Similarly, square root of 2, which is not a rational number, but it also divides the set of all those rational number whose square positive rational number whose square is less than 2, and set of all rational number whose is positive rational number whose square is greater than 2. So, this way we are able to introduce the concept of the rational and irrational also. So, let us formalize this part. The section of rational number, what do you mean by that first? The mode of division of numbers into two classes, which is described just now, is known as the section or cut. So, the mode of division of numbers into two classes in different way is known as section or cut of numbers. Clear? In general, the section of the rational number section of a rational number of rational numbers, the section of a rational number can be constructed with the help of any two properties say p and q, which are mutually exclusive that is disjoints, exclusive, and one of which is essentially possessed by every rational number. The meaning of this is, suppose we have a set of rational numbers, a collection of the rational number. I introduce the two properties on it. One is p, another one is q. So, suppose p is the property set of all rational number which are less than or equal to say 2, and q is a property set of all rational number which are greater than 2. So, what happens, the entire rational number can be divided into the two classes now. Clear? Those number which are less than or equal to 2 and the number which are greater than 2, and 2 is the number which is responsible for dividing the entire class into entire numbers into 2 sections. So, this 2 becomes the section or cut of the race, okay, and this section L R will be the cut corresponding to rational point 2. Similarly, the number square root 2, that is also a number which can divide, which can bifurcate the entire collection of the rational numbers into 2 parts. Those numbers which are whose positive rational number whose square root is less than 2, and those positive number whose square root is greater than 2. So, 2 is greater than root 2, sorry, greater than square is less than 2 and square is greater than 2. So, root 2 will be the number, that one. Now, in this way we are basically dividing the whole thing into 2 classes. The class where the every number in the class, if it is less than the number of the every number of the class R, then we say L is the lower class, R is the upper class, or we can say a number which possesses the property P is less than the number which possesses the property Q, then the property P will generate the class which is denoted by L and is known as the lower class, and the property Q which generate the class is denoted by capital R and we call it as the upper class. Clear? So, this way we are having the 2 class, lower class and the upper class. Is it clear now? So, we can say like that, if every number which possesses the property P, is less than every number which possesses the property Q, which possesses the property Q, then the former shall constitute the class denoted by L, and the latter one will constitute the class denoted by capital R, okay, denoted by capital R. And the examples we have seen already, that the L is the set of those rational number x, which Q is the rational number, remember, okay, Q is already there. So, do not write it, rational numbers, collection of rational numbers such that x is less than equal to 1, and R is the class of those rational points, rational numbers such that x is greater than 1. So, this is the property P, is it not? This one is the property P, this one is the property Q. Now, you see both the property are exclusive, mutually exclusive. A point, you cannot get a rational number which belongs to P as well as in Q. If it belongs to P, it cannot be in Q. And second one is every point in P is less than the every point in Q, the property which satisfies the property Q. So, this will be hence this entire be denoted by LR, and this, since this corresponds to 1. So, we say the one rational number corresponds the section LR, 1 corresponds to this section LR. Is it okay? Like this. Okay. Okay. Similarly, if I take L is the set of all negative rational rationals 0 and those positive rationals whose square is strictly less than 2. So, okay. The property I am putting here only, I am adding minus all rational and 0, but property is basically those positive rational number whose square is less than 2, clear. And this in this class we are introducing the negative as all negative and 0, and R is the set of all rationals such that square of this is greater than 2. All positive rationals, all positive rationals whose square is greater than 2. So, now all these rational number will be filled up here, and this class which we denoted by is nothing but correspond to square root class, clear. Is it okay? Now, the difference between this and these two class is, in the earlier case one is a rational number, and what is the property which enjoy by a rational number is, then one must be, or rational number which correspond to a section L R must be a point either in L or in R. Is it not? Any number which corresponds to a section L R must be a point in either lower class or in upper. Once it is in the lower class, then it becomes the largest number. L lower class will have the largest number equal to say 1 here, and once it is in R, then it has the least number in that. But in case of the section which correspond to the irrational points, here none of these lower and the upper class has a largest or least number. We cannot have it. Okay? This does not belongs to neither L nor R, but it divides the whole rational numbers into two parts. The third case is, we cannot choose the property P and Q as follows. For example, suppose I take the property P is the set of those rational x such that x is strictly less than 1, and if I choose a property Q, those rational such that x is strictly greater than 1. Okay. Why we cannot choose this? The reason is, by taking this type of property, it gives the lower class and the upper class, fine. All the numbers, rational number which are less than 1 will form a lower class, all the number which are less than greater than 1 will form the upper class. But what about the number 1? Is neither belongs to lower class nor the upper class. Okay. So, we are loser, we are not including all these, is it correct? So, all the rational number cannot be covered. Similarly, a rational number note in case of the if the lower class L, and the upper class capital R cannot have simultaneously greatest rational number, say L, and least rational number say R respectively. What is the meaning of this? Let us see first, explain this part. What I mean is, suppose we have this is our lower class, this is a upper class. What I am saying is that it is not possible to have the largest number upper lower class will have a largest number, as well as upper class will have a lowest number. It is not possible. One of the class, if lower class have a largest number, upper class cannot have a lowest number, and vice versa. If lower class does not have an upper largest number, then lower all will have a least number, lower number, least number. Why? If suppose it is true, it means L number which is the largest belongs to L, R number which is the least belongs to R. It means the number lower than R will not be available in capital R, the number which is greater than R will not be available in L. So, what happened to between L and R? Between L and R, because L plus R by 2 is a number neither belongs to R or L or null R. So, there are infinitely many numbers will be left out in between L and R, which does not occupy the position neither in L nor in R. So, it means our section of all rational number is not complete. We are not able to adjust all the rational number in one of the class, is it not? Some rational number are out. So, this way the division is not comfortable, is not permissible. So, that is why what we say, we cannot have a property like this, which can leave many of the rational number without putting either in R or in L. Is it okay? Clear. So, this is one. Now, it may possible that there may be only one class, other class may not exist. There may be possible. Suppose I take all the rational numbers, get say positive, negative and 0, they are all belongs to one class. That is all. All the rational number which are less than infinity, it form the lower class suppose. You cannot have it upper class. So, there is a possibility that we can have out of these two, lower and upper, we have only one, but that is not the case which we are dealing. In fact, it is the only case when minus infinity or plus infinity is taken in consideration, is it not? Suppose I want to introduce infinity or minus infinity, then this type of possibility is there. But what we are dealing is here is, we are taking only the finite rational numbers, where we always exactly have the lower class and the upper class, and this section LR, the cut is denoted by a number alpha, which is a either rational number or maybe the real irrational number. Is this clear? So, this way we are. Now, if we have combined with this, then what we get finally is that we are having section of three numbers. One is three types of the classes, that is, one is the lower class has a largest number, upper class has no lowest number. Second class is the largest, lower class does not have a largest number, upper class has a lowest number, and third case none of the class has neither upper nor lower. So, first two class correspond to a rational number, while the third class correspond to the irrational number, and this is the way Dedekind has introduced the concept of the irrational number in the number system. Okay. So, that is why Dedekind's introduction of rational, Dedekind's way of introducing irrational number. Okay. So, what is a section of real number? Since sections all cut of rational numbers are of three type. The first type is the class L, has a greatest number say L, and the class R has no least number. This is the one type. Second type is the class L, the class R, not L, the class R has a least number, say R, and the class L has no greatest number. And third type of this is the class L. The class L has no greatest number, and the class R has no least number. Okay. So, first two types clearly, type 1 and 2 corresponds to rational numbers L and R respectively, while type 3 gives a irrational number or corresponds to a irrational number. And this is the way Dedekind said introduce the concept of irrational number. Okay. Is it clear? So, what one more thing which we can observe from this type, that if we pick up any real number, it will always be represented by means of the section LR. So, any real number can be represented as a section LR, lower class and upper class. Now, this section, if it falls in the first two category, then real number becomes the rational, it will represent the rational point. If it falls in the third category, then that real number will be the irrational points. Okay. So, now we can say thus any real number alpha can be defined by means of section LR. Is it okay? So, that is what is okay. Now, okay. we have started with the rational numbers only, okay. And then while introducing the section, we have come across about the irrational points. Okay. So, thus this way we have developed the sections which represents the rational number, and sometimes it also represents the irrational number, is it not? So, if we consider the collection of all these sections, aggregate sets of all these sections, then this set of all these sections will be the bigger class than the set of rational number. Why? Because this sections, collection of this section represents either the rational number or real number, and every rational number can be represented by means of this section, or every section represents some rational points, but as well as there are sections which also represent the irrational points. But here right hand side we are taking only the set of rational numbers. So, it means the aggregate of this section is much bigger than the aggregate of the set of rational number, is it not? and that gives the concept of the real numbers. Okay. So, Dedekind this way has extended the system of the extended the rational numbers into a real number by introducing the irrational point in between. Is this clear? So, this is the known as the Dedekind's theory. Okay. So, let us see the what is the Dedekind's theory is. Dedekind's theorem. Okay. This is the Dedekind's theory. Okay. Same way. So, since the aggregate aggregate all the set of all rational points, aggregate of sections of rational numbers is a larger aggregate than that of rational numbers. Themselves. So, it includes the section corresponding to all rational number, and thus we define the number corresponding to the additional section, and thus the numbers corresponding to this additional section additional sections are defined as irrational number. Okay, that is what is. So, we have now this Dedekind theorem. Now, before going something else, let me just write down what is the Dedekind's theorem. If the system of real numbers is divided into two classes, L and R, in such a way that one, each class contains at least one number. Second, at least one number. Second is every number belongs to one class or the other, and third proper condition is, and third part is every number in the lower class L is less than alpha is less than every number in the upper class. Every number in the upper class R, then there is a number there is a number alpha such that every number less than alpha belongs to L and every number greater than alpha there is a number alpha such that every number less than alpha belongs to N, every number greater than alpha belongs to R. Then alpha belongs to R. The number alpha itself, may belong to either class. Same thing which we have written, means we have a set of real numbers. Now, what we did it that this set of number divided into two parts, lower class and the upper class, and which has the property that every member each class contains at least one real number. Second is every member in the lower class belongs to one each class contains at least one and every number belonging to one class or the other, and third is every number in the lower class is less than the every number in the upper class. Then the number alpha is such that every number less than alpha belongs to L, while the every number greater than alpha belongs to R. Now, what happened to alpha? What he says is the alpha itself may belongs to either class. So, when he say may belongs to alpha, it means there is a hidden thing. If alpha is a rational number, then it will belongs to one of the class, it has to belongs to one of the class, as we have seen. But if alpha is a irrational number, then it will neither belongs to L nor belongs to R. So, that is what he has developed the. Okay. Now, the question is when he started with this cuts, and with the help of the cut he has introduced the concept of the generalized the set of rational number and introduced the concept of rational number. Then with the help of the cut, how did he justify the addition, subtraction, multiplication, division? Because when you take the two real number, the addition of the two real number is again a real number. So, it should represent some by a some cut. Subtraction is also real number, division is also real number provided it is non-zero, and like this reverse. So, he has also introduced the way the addition of the two cuts is how to define, subtraction of the two cuts to define, the reciprocal of the cut how it is defined, and like. So, we will take up first those what are these definitions. Okay. So, the relation of magnitude for m. So, we can define introduce or definition of addition, subtraction, division, multiplication in terms of cuts using cuts or sections. Okay. How to define? Okay. How to define this thing, okay, definitions. Okay. Let alpha 1, let alpha 1 and alpha 2 be two real numbers. Two real numbers given by the section, giving by the section all cut, you can say section L1 R1 and L2 R2 respectively. Okay. Respectively. Now, we say number 1, if every member of, there are three possibility, there are three possibility, Number 1, first possibility is every member of L1, every member of L1 belongs, every member of L1 belongs to L2 and every member of R1 belongs to R2. This is the first possibility. Okay. The second possibility is, okay, the second possibility is every member of L1 belongs to L2 and every member of R1 and belongs to, but every member of R1, but every member of L1 belongs to L2, but every member of R1 does not belongs to R2. This is second possibility, and third possibility is every member of L1 does not belong to L2 what? But every member of R1 belongs to R2. Okay. So, let us see this. This is first case. Suppose these are two classes. This is two. This is our L1, this is R1, this is L2, this is R2. Now, what it says first class, if first possibility is every member of L1 belongs to L2 and every member of R1 belongs to R2. So, that is only possible when basically L1 coincide with L2, R1 coincide with R2. So, if this is alpha 1, here is alpha 2. So, here the case is alpha 1 equal to alpha 2, is it not? Then second case is case 2. Here say this is our L1, here is R1 and say here is this L2 and this is R2. So, here this is alpha 1, here is this alpha 2. So, second case says that if every this one, every member of L1 belongs to L2. So, every member of L1 belongs to L2. It means the cut alpha 1, all these entire line must be lying on part of L2, but every member of R1 does not belongs to R2. It means the R1 class supersede the R2, is it not? So, that is only possible when the position of alpha 1 and alpha 2 is such that alpha 1 is strictly less than alpha 2. Okay? Then third case is if we take say L1 R1, this is alpha 1 and this is alpha 2 L2 R2. So, every member of L1 does not belongs to L2. So, it means L2 is a subset of L1, but every member of L1 is contained in. So, the position is alpha 1 is greater than alpha 2. So, the if two numbers alpha 1 alpha 2 are given, then one can order them that they are either equal or one is less than the other or it means the set of real number is basically an ordered set field. One can easily identify the ordering between the two and with the help of our cuts also. Is it okay? So, that is what. Then in a similar way, he has introduced the positive, negative and 0 number. Positive, negative and 0 number in terms of the cuts. The real number alpha given by the section LR given by the section LR is said to be positive if or when the lower class L contains some positive numbers. It means that is lower class L will contain all negative, zeros and some positive. Is it okay or not? Some positive. That is, if this is a line, then a number alpha will be a positive number if basically it is greater than 0. So, here it is 0 and rest are minus 1, minus 2 etcetera. So, this lower class must contain some positive numbers, then only alpha will be treated as positive greater than 0 or positive. Similarly, the alpha is negative means what? The real number alpha is said to be negative when the upper class R contains some negative numbers. That is obviously true. If here is L, this is 0, here is L, this is R. If R contains some negative number, then only the number correspond to this will be a negative number, is it not? The real number is said to be negative when the upper class R contains some negative numbers. So, L is totally negative and R contains some negative numbers. So, the corresponding to say minus 1, this will be the cut, okay, like this. And 0 means what? And if all the numbers in R, if all the numbers in L are negative and all the numbers and all those in R are positive, then the real number defined by the section is 0, obviously, clear. So, there nothing is very simple.
So, alpha is the means determining point between the L and R.
Okay. This is clear. So, this is alpha somewhere, negative was like this. Then addition, subtraction, etc., can be done. If suppose alpha is the lower class, then how to define this number? If alpha correspond to the lower class L R, then minus alpha correspond to minus R minus L, that is all, clear. This is the class alpha, lower and upper. If minus alpha means change the sign of elements of R and make it at the lower class, and change the sign of L with minus and make the upper class. Now, what the difference will come if L has a greatest number, alpha has a greatest number in lower class, has a cut alpha where the lower class L is greatest number, then minus alpha here upper class will have the least number, that is all. Suppose I take L to be less than equal to 1, then 1 is the greatest number in the lower class. When you find minus 1, what happens to this? Minus 1 becomes here the least number, is it not, for the upper class. So, similarly, if alpha is there, then 1 by alpha we denoted by 1 by R, 1 by L. All the property remains the same, similarly other. So, for positive, for negative and for negative also, we can write minus 1 by alpha as minus 1 upon minus alpha, okay, like this, clear. Take minus and then reverse it, we get. So, all this means decision, the algebraic operations can be also justified by using the our cuts system. Okay. So, that is what is there. Then sum and difference, if suppose we get the alpha 1 is one cut L 1 R 1, alpha 2 another cut L 2 R 2, then sum of this alpha 1 plus alpha 2 is a cut correspond to alpha 3, that is L 3 R 3, such that any number alpha 3, any number A 3 belongs to L 3 can be written as A 1 plus A 2, where A 1 belongs to L 1, A 2 belongs to L 2 for sum. Similarly, R 3 B 3 belongs to R 3 can be written as B 3 as B 1 plus B 2, where the B 1 is an element in R 1, B 2 is an element in R 2.
Sir, in upper case means minus 1 by alpha is equal to 1 divided by minus alpha.
This one?
No, sir.
This?
Next.
Minus.
1 by alpha is equal to 1 divided by
minus
alpha. So, to get the minus alpha, we have to use the
first you take this one, then reverse it.
Okay. When we will reverse it, then this will come here, means
again it will come minus 1 by R. So, it will reverse again the things. Okay. So, that will be come. Is it okay? No? Minus 1 by alpha. In fact, it is the same as minus 1 by alpha. Is it not? minus 1 by alpha and then reverses. 1 by alpha will be this, then minus 1 by r and 1 by r. Now, if we take minus this, minus means this, reverse it. So, minus 1 by r here, same thing will come. Now, here also addition can be done like this, is it not? What is the meaning of this addition is, suppose we have this alpha 1 cut L 1 R 1, alpha 2 is this cut L 2 R 2. When we add this thing, this is alpha 1 plus alpha 2, we denote by alpha 3. So, this is L 3 R 3. Now, if I take any point A 3 here, then corresponding to we get a point A 1 here, A 2 here, such that A 1 plus A 2 becomes A 3. Similarly, if we take B 3 point here somewhere, is it not A B 3, then we can find out B 1 here, B 2 here, such that B 3 can be written as B 1 plus B 2. Clear? Yes. Similarly, subtraction, multiplication and other. So, we are not going this thing. If we find the multiplication, in a similar way you can write the multiplication and division. Is it okay? So, we are not going for the detail. Okay. So, then between any two real number, there are infinite number of real numbers, one can easily prove, just like between any two rational number, there are infinite rational number is there. So, between any two real number, one can always find the name. So, between any two, some result, the result is between any two real number, between any two real numbers, there are infinite number rational numbers. Second result is between any two real numbers, there are infinite number of irrational point. Number of irrational numbers, infinite number of rational points, infinite number of irrational points numbers. In fact, this I will prove it, but just I will give a hint how to. Suppose there are two numbers, real numbers, alpha 1 and alpha 2, there are two numbers. This is alpha 1, this is alpha 2, L 1 R 1, L 2 R 2. So, between these two number L 1 alpha 1 alpha 2, there are infinite number of rational point. Why? Because L 1 alpha 1 is less than alpha 1 and alpha 2 are given, one can easily identify either alpha 1 less than alpha 2 or alpha 1 is greater than alpha 2 or maybe equal. Suppose less than alpha 1, then every element of L 1 is the element of L 2, but every element of R 1 is not this. It means, some of the point R 1 is also in L 2. So, if I take any point A 1 here and here is say B 1, then these are also the point here L 2, and L 2 is the collection of all the number which are less than alpha 2. So, in between those we can still find the rational number. So, there are infinite rational number can be introduced similarly. Okay. So, we will do it this result. Thank you very much. Thanks.